Welcome again. And this is also a problem related to the motion of charged particle in an electric field. However, this electric field is produced by a long wire. So let's read the statement of the problem first. It says a charged particle moves with the kinetic energy K past a long uniformly charged wire. Perhaps this is the long charged wire and its front view is shown here, and the particle travels in a plane perpendicular to the wire, yes of course, and deviates from its initial path by a small angle. Alpha angle is small. Okay, find alpha assuming that the particle's charge is E. It must be positive or maybe negative if it is negative too. So I have assumed both the charges negative. The uniformly charged wire is positively charged, and this charge Q is also positive. And the ring of a unit length of wire and the charge of a unit length of the wire is lambda. That means charge per unit length is lambda. At a distance r from the wire, the electric field is, of course, it's a well-known value. That is lambda by 2 pi epsilon naught r. So this is the problem. We have to calculate the small deviation angle of deviation. It seems to me a standard problem, and I can see that the charge E is being repelled by the wire when it comes close to it. However, if I take this point as point A, suppose that well, it can be anywhere. It can be anywhere, but leave it. I'm not going to suppose anything right now. I will try to solve this problem simply thinking that at this moment here, when it started deflecting, its velocity is v, and I will take an x-axis like this and y-axis are like this, and x-axis along the line of motion of the charge and y-axis perpendicular to it, and its velocity here when it started deflecting is v, and the angle made by velocity vector with x-axis is alpha. So I can simply tell this velocity vector has two components. One is x component vx and another is y component vy. So that I can write something like tan alpha is equal to vy upon vx. And since alpha is quite small, I can write approximate tan alpha to alpha, and I can write alpha is simply equal to vy upon vx. And it seems reasonable. So this charged particle has two components, Vx and Vy. Vx and Vy. And I guess that this velocity component Vx is obtained from the kinetic energy K, because the particle possessing before coming under the influence of the wire is the velocity component Vx. And I can also think that the y component of velocity is acquired by the particle due to the influence of the field produced by the wire. Then I can write simply Vx. Under this assumption, I can write Vx will be under root 2k by m. You're simply using k equals half md square. I wrote this result, and the formidable task is to find the y component of velocity, that is vy, and it can be found using Newton's second law of motion. And I can write something like Fy equals m dvy upon dt, and Fy here is force. The electric field due to this will be from the wire will be in this direction here, so it is exerting on a repulsive force here as E if the electric field here is this. And I would like to take this angle simply by something else. Suppose that I took this angle as psi. Yeah, so if this angle is psi, this angle is also psi, so the force Fy acting here will be E cos psi. Yeah, E cos psi. So I can write here, I would like to write this equation simply as Fy dt equals m dvy, and Fy I can see, I can write it like E cos psi. Yeah, and so that it can be written as I am writing Fy like this, and Fy E, and value of E is given in the problem, as you can see it. It is 2 pi epsilon naught r multiplied by cos psi, and this becomes Fy. Okay, fine, I got Fy. What about dt? How can I find the value of dt? And we have a relationship. I haven't used Vx yet. I can write Vx equals dx by dt, so that dx is a very small length in this direction, or say, look, I have to remove something. Yeah, it was fine, but yeah, these things can be removed. These things can also be removed, so that I can show you there is a small length dx, and I would like to write Vx equals dx by dt. But the main problem is, how can I find a relation between dx and other things, like other important things, like the distance from this distance is r, and this angle is psi. That means this angle, I guess, will be very much a small angle, and I would like to write it as well, this is a small length dx, and this length is r, and this length, this angle, I'm willing to call it d psi, because this whole angle was psi. And so I can take this length as this, not this length, I want to write this length as RD psi, and this length is dx. You can see here, so that angle between this is along y-axis, this and this, and this line is perpendicular to this line, and this line I suppose is perpendicular to this line. So this angle is also going to be psi, d psi. This angle is also going to be d psi. So I can write here dx cos psi will be equal to rd psi, and I can write dt equals dt equals dx by vx. I should not have lost my control, otherwise I am not going to solve it. Dx upon vx. So I guess now dx I can write r d psi upon cos psi, and vx will be here. So dt I should write like this, and fy like this. And what about this relation? Can I think I'm ready to use this relationship, and well, I can use, we have fy dt equals m dvy. This was the relation, and this should have been fy dt equals m dvy, and I can write here fy equals e lambda by 2 pi lambda upon 2 pi epsilon naught r, capital R, cos psi, not phi, and dt equals r d psi upon vx, whose value is given and it's a constant, cos psi. So you can see here cos psi gets cancelled out, and we have a good relationship, that is, and this thing is equal to m dvy. That is why I should write dvy equals e lambda by 2 pi epsilon naught m r, m I taken to the right side, and r also gets cancelled out. R also gets cancelled out. That means we have only d psi left, and vx in the denominator, and d psi in the numerator. Well, and this is a relation in differentials, so we should integrate this. So dvy, it was initially 0 and it had just got into vy, and now too many things are going to out from this integration symbol, almost all of them except the d psi. And d psi is the angle made by this wire, and no problem at all. The psi has limits from minus infinity because wire is infinite, so this psi has limit from minus pi by 2. The angle is, and this psi is the angle, that is angle psi lies from minus pi by 2 to pi by 2. And what we got next, it's number of pi to get out from our equation. So we got Vy equals E lambda by 2 epsilon naught m Vx. Oh, so Vy is this, and I got it. Angle alpha is simply Vy upon Vx, and Vx gets cancelled out, and the answer is E lambda by 2 epsilon naught m, and that's solved. That no, I didn't do it. This is Vx square perhaps. Lambda by 2 epsilon naught m Vx square, and well, kinetic energy was given, so this half m Vx square was the kinetic energy. That means half 4. That means the answer we are looking for is E lambda by 4 epsilon naught k, and that is the final answer for you. Thank you very much for watching.